Module 32, Lecture B, Production Integration. By the end of this lecture, you will be able to design production-ready pipelines with consistent preprocessing and leakage prevention. Use output configuration, feature names, and array handling to integrate with downstream systems. And plan and evaluate a capstone Scikit-Learn project from data framing to validation. Reliable pipelines, consistent preprocessing. Reliable production models need the same preprocessing used during training. Steps like scaling, encoding, and filling missing values should not be handled separately, because small differences can make predictions incorrect. A strong pipeline combines preprocessing with the model, so every new input follows the same validated transformation process. Consistent preprocessing keeps feature meaning stable from experimentation to production. Any transformation used during training, such as filling missing values or encoding diagnosis codes, must be applied the same way to new data. This repeatability prevents errors and ensures the full path from model fitting to prediction remains controlled and reliable. Consistent preprocessing is essential for reliable machine learning systems. A clear pipeline shows how raw data becomes features, making models easier to monitor, retrain, audit, and share across teams. It also helps ensure that changes are controlled, and that training and production data are handled the same way, reducing deployment risks. Python code, consistent preprocessing. This example creates a reliable preprocessing pipeline by learning all transformation rules from the training data only. The same learned transformations are then applied automatically to any new rows. The code imports key libraries for a machine learning workflow. NumPy supports numerical work and missing values. Pandas handles tabular data analysis. And Scikit-Learn provides tools for building and evaluating models. Together, these imports prepare the environment for data preprocessing and model training. We import key Scikit-Learn tools to build a complete machine learning workflow. The ColumnTransformer, Imputer, OneHotEncoder, and StandardScaler handle preprocessing, including missing values, categorical features, and feature scaling. Train test split separates the data for training and evaluation. Logistic regression provides the prediction model, and accuracy score measures performance. A pipeline connects these steps, so preprocessing and modeling run consistently together. We create a small pandas data frame to demonstrate machine learning preprocessing. It includes customer age, account balance with some missing values, plan type as categorical data, and a churn indicator showing whether each customer left. This mix of numerical, categorical, binary, and missing data makes it useful for practicing common preprocessing steps. We prepare the data by separating the model inputs from the outcome to predict. The inputs are customer details such as age, balance, and plan, while the target is whether the customer churned. This separation helps the machine learning model learn from the features and predict the correct outcome. We use Scikit-Learn's train test split function to divide the data into training and testing sets. 1/3 of the data is kept for testing, and a fixed random state makes the split reproducible. Stratification keeps the class proportions consistent in both sets, so the target distribution remains balanced. A numeric data pipeline applies the same preprocessing steps consistently to all numeric columns. It first fills missing values using each column's median, then standardizes the values by centering them and scaling to unit variance. These steps help prepare the data for machine learning algorithms that depend on well-scaled numeric inputs. A categorical data pipeline uses one-hot encoding to convert categories into a machine learning-friendly format. It is set to ignore unknown categories in new data helping the model handle unexpected values. The transformed output is made dense, so it appears as a standard array for easier use in later steps. A ColumnTransformer applies the right preprocessing to each type of data. Numeric columns such as age and balance are imputed and scaled, while the categorical plan column is OneHotEncoded. This lets the preprocessing run automatically and consistently for each column type. A pipeline combines data preprocessing and model training into one consistent workflow. It handles missing values, scales numeric features, encodes categorical features, and then trains a logistic regression model. Setting a random state makes the results reproducible, while the pipeline keeps the process efficient and consistent. Fitting the model pipeline on the training data lets it learn both preprocessing steps and model parameters together. This includes handling missing values, scaling numeric features, encoding categories, and training the logistic regression model. Treating the pipeline as one unit keeps these steps consistent and ready to apply to new data. The test data is preprocessed using the same rules learned from the training data, keeping the workflow consistent. The full pipeline then uses the logistic regression model to make predictions, and the accuracy score measures how closely those predictions match the true test labels. We create a small data frame for one new customer to test the preprocessing pipeline. The customer has age 50, a missing balance, and an enterprise plan, which checks how the pipeline handles missing data and an unseen category. A pipeline combines preprocessing and the model to make consistent predictions on new data, even when a row has missing values or unfamiliar categories. It applies the same transformations learned during training, before predicting whether the customer will churn. We can also inspect the transformed feature names from the preprocessing step to understand what inputs the model actually uses. The output summarizes key checks and results from a Scikit-Learn churn model. It reports the library version, the training and test split sizes, the model's test accuracy, and the number and sample names of features created during preprocessing. It then applies the model to a new customer to predict whether that customer is likely to churn. This script shows a complete Scikit-Learn preprocessing and modeling workflow. It builds a small dataset with missing and categorical values, splits it into training and test data, then imputes and scales numeric features, while OneHotEncoding categorical features. These steps are combined with logistic regression in one pipeline, which is trained and evaluated on test accuracy. The script also applies the same pipeline to a new customer with missing and unseen values, then reports key outputs such as feature count, feature names, and the churn prediction. Prevent data leakage. Preventing data leakage is essential when building machine learning pipelines for production. Leakage occurs when training or validation uses information that would not be available at prediction time, causing performance to look better than it will in practice. To avoid this, every feature and transformation should be checked to ensure it is truly known and accessible when the model makes its decision. Data leakage can occur when preprocessing uses information from validation or test data. To avoid this, fit scalars, encoders, and similar tools only on the training set, then apply the learned settings unchanged to other data. This keeps performance estimates realistic and better reflects how the model will behave on new unseen data. To prevent data leakage, make sure your training and testing data respect time, grouping, and real-world context. Do not train on information from the future. Keep related records from the same entity together, and avoid features that reveal the outcome indirectly. Good leakage prevention requires both careful technical setup and a clear understanding of when and how the data was created. Python code. Prevent data leakage. This example highlights how preprocessing done too early can leak test information into training. Using a pipeline prevents that leakage, and the reported scores show the difference between leaky and safe workflows. This setup imports the main Scikit-Learn tools needed to build and evaluate a simple classification workflow. It includes a function to create synthetic classification data, feature selection using ANOVA-based scoring, logistic regression for binary classification, and accuracy measurement. It also imports tools to split data into training and testing sets, and to combine preprocessing and modeling in a pipeline, which helps prevent data leakage. We create a synthetic classification dataset with 600 samples and 200 features using Scikit-Learn. Only 5 features are truly informative, while the rest are noise, making it useful for showing how data leakage can falsely inflate model accuracy. A fixed random state keeps the results reproducible. The code first verifies that the features data has the expected size of 600 rows and 200 columns. If the dimensions are wrong, it raises an error to flag the problem early. This check helps confirm the data was generated correctly before modeling begins. First, the dataset is split into training and testing sets using Scikit-Learn's train test split function. 30% of the data is reserved for testing, with stratification to keep the target distribution consistent in both sets. A fixed random state makes the split reproducible. This keeps the test data unseen during preprocessing and training, helping prevent data leakage. This code demonstrates a leaky approach to feature selection. It uses a select k-best selector with an F classification score to choose the 10 features most related to the target, then fits and transforms the entire dataset at once. Because the selection uses information from both training and test data, it can overfit and produce performance results that look better than they really are. The leaky features and target are split into training and test sets using a train test split function, with 30% reserved for testing. Stratification keeps the target distribution consistent, and a fixed random state makes the split reproducible. This example highlights the problem of letting preprocessing expose the model to test data, which a safe workflow must avoid. A logistic regression model is trained on leaky training data, meaning the preprocessing has already exposed it to information from the test set. Its accuracy is then measured on the leaky test data by comparing predictions with the true targets. Because of this data leakage, the reported performance may be overly optimistic. A pipeline helps prevent data leakage by keeping feature selection and model training in the correct order. It first selects the 10 best features using an analysis of variance classification score, then trains a logistic regression model with reproducible settings. Because feature selection happens inside the pipeline, it is learned only from the training data and does not use information from the test data. Train the pipeline only on the training data so preprocessing does not use any information from the test set. Then use the fitted pipeline to predict the test data, which measures performance on unseen examples. Comparing those predictions with the true test targets gives an accuracy score that shows how well the model generalizes. The code compares model accuracy with and without data leakage. It first reports the Scikit-Learn version, then shows that leaky preprocessing can make test accuracy look too high because the test data influenced feature selection. Using a pipeline avoids this by applying preprocessing only within the training process, giving a more realistic performance estimate. The key lesson is to split the data before fitting preprocessing steps and use pipelines to prevent leakage. This script shows how data leakage can make a machine learning model look better than it really is. In the leaky workflow, feature selection is done before the train test split, so information from the test data influences preprocessing and inflates accuracy. The safer workflow uses a pipeline, So feature selection and training are fit only on the training data, giving a more realistic result. The main lesson is to split the data before preprocessing and use pipelines to prevent leakage. Controlled randomness. Controlled randomness helps make machine learning results consistent and trustworthy. Because steps like data splitting, feature selection, and optimization can change between runs, random choices should be made repeatable by using fixed seeds. This makes experiments easier to compare, helps explain unexpected changes, and ensures the deployed model matches the version that was tested. Controlling randomness is important when evaluating models because different data splits can change performance results and lead to misleading conclusions. Fixing the random state makes comparisons across preprocessing choices, algorithms, and hyperparameters consistent. Still, teams should use repeated validation or cross-validation to tell real improvements apart from random noise. In production machine learning, controlling randomness is essential for reproducibility, governance, and incident response. Fixed randomness helps ensure that different teams or environments train the same model from the same data, preprocessing, and settings. This is especially important when small model changes can affect real decisions, such as in credit scoring or fraud detection. At the same time, pipelines must adapt to changing production data and monitor performance so randomness remains useful rather than unpredictable. Python code. Controlled randomness. This example explains why fixed seeds are important. By controlling randomness, you can make pipeline results repeatable and compare unstable evaluations with stable ones. We import key Scikit-Learn tools to build and evaluate a simple classification model. The breast cancer dataset provides the data, while the train test split function separates it into training and testing sets. A pipeline combines standard scaling with logistic regression, so the features are normalized before modeling. Finally, the accuracy score function measures how well the model's predictions match the true labels. We load Scikit-Learn's built-in breast cancer dataset for a classification task. The dataset provides both the input features and the target labels, which are separated so they can be used for later processing and model training. The code verifies that the feature data and target labels have the same number of entries, so every data point has a matching label. If they do not match, it raises an error to stop the process. This early check helps protect data integrity and prevents problems later in supervised learning. A pre-processing and modeling pipeline combines feature scaling with logistic regression in one repeatable workflow. The scaler standardizes features to have a mean of 0 and a standard deviation of 1, while logistic regression is given enough iterations to converge. Keeping these steps together improves consistency and helps prevent data leakage. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is reserved for testing, and stratification keeps the class distribution consistent with the original dataset. Because no random state is set, the split can change each time the code runs. The pipeline is trained on training split A by fitting the model to its features and labels. It is then tested on the matching test split, where predicted labels are compared with the true labels using an accuracy score. This shows how well the model performs on unseen data from that split. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is reserved for testing, while stratification keeps the class proportions similar in both sets. Because no random state is set, the exact split can change each time the code runs. The pipeline trains a logistic regression model on the training data, so it can learn the relationship between the features, and the target labels. Its performance is then measured by predicting labels for the test data and comparing them with the true labels. The resulting accuracy value shows how well the model performed on that test split. We use Scikit-Learn's train-test-split function to divide the data into training and testing sets, with one quarter reserved for testing. Stratification keeps the class proportions the same in both sets as in the original data. Setting a fixed random state makes the split reproducible, so results stay consistent across runs. The pipeline is trained on labeled training data, so the model can learn how features relate to labels. Its performance is then evaluated by comparing the true test labels with the model's predictions on unseen test data, producing an accuracy score. The dataset is split into training and testing parts, with one quarter reserved for testing. Stratification keeps the class balance similar in both parts, matching the original dataset. A fixed random state makes the split reproducible each time the code runs. The pipeline is trained on the selected training split by fitting the model to its features and labels. Its accuracy is then measured on the matching test split by comparing predictions with the true labels. This evaluates how well the model performs on unseen data, while keeping the results tied to the controlled random split. The output first confirms the Scikit-Learn version to support reproducibility. It then compares uncontrolled data splits, where accuracy can change because of randomness, with controlled splits that use a fixed random state and produce consistent results. Finally, it verifies that the controlled test sets match, showing that the split is reproducible. This script shows why fixed random seeds matter for reproducible machine learning results. It trains a scaled logistic regression model on a breast cancer dataset and compares repeated train test splits with and without controlled randomness. Without a fixed seed, the test sets and accuracy scores can change between runs. With a fixed seed, the splits match and the results stay consistent, demonstrating how controlled randomness supports repeatable experiments. Output integration. Pandas output configuration. Configuring Pandas output helps make transformed data easier to understand and safer to use in production. Unlike plain numerical arrays, Pandas-style tables preserve column labels and index information, so features remain tied to their business meaning. This supports inspection, logging, and reporting, and reduces errors when pipelines change. In production, Pandas output helps keep transformed data consistent across training, validation, and real-time inference. Because columns stay labeled, engineers can confirm that each feature keeps the same meaning across system handoffs. This reduces the risk that pre-processing changes silently shift data meanings, and it makes mismatches easier to catch during validation and review. When configuring Pandas output, choose the format deliberately. Labeled tables help with clarity, debugging, and monitoring, while numerical arrays are often better for speed and large datasets. Teams should use labels where they add value, such as development or offline analysis, and prefer arrays in high-performance production paths. This balance makes data pipelines easier to maintain and less likely to fail silently. Python code. Pandas output configuration. This section shows how Pandas output can make pre-processing pipeline results easier to interpret. It focuses on preserving feature names after applying mixed transformations, so the transformed data remains labeled and understandable. It also compares this labeled output with plain arrays, highlighting the value of keeping feature names attached. We import Pandas for working with tabular data and Scikit-Learn tools for pre-processing. A column transformer lets us apply different transformations to different columns, while a pipeline keeps the processing steps organized and consistent. OneHotEncoding prepares categorical features for machine learning, and standard scaling puts numerical features on a comparable scale. We create a small customer table in pandas, using a data frame, a standard structure for tabular data in Python. It includes customer tenure in months, monthly charges, and contract type, such as month-to-month, 1 year, or 2 year. This simple setup makes the customer data easy to analyze and manipulate in later steps. We separate the input features by type, so each can be processed correctly. Tenure months and monthly charge are treated as numeric features, while contract type is treated as categorical. This setup lets the transformation pipeline apply the right preprocessing to each kind of data. A ColumnTransformer lets us apply different preprocessing steps to different types of data. In this case, numeric features are standardized so they have a mean of 0 and a standard deviation of 1, while categorical features are converted into binary columns using OneHotEncoding. The output is made dense for easier handling, and the combined transformations keep each resulting column's meaning clear. A pipeline is created to organize the data preprocessing steps, using the previously defined preprocessor to handle both numeric and categorical features. The pipeline is then fitted to the customer data, so it can learn any needed transformation settings, such as scaling values. After transformation, the result is an array of processed features ready for analysis or modeling. We create a pre-processing pipeline and configure it to return a pandas data frame rather than a default array. This keeps the transformed customer data labeled with its column names, making the output easier to interpret. The pipeline is then applied to the customer data, and the transformed result is stored for later use. Check that the transformed pandas output has the same number of rows as the original customer data. This confirms the transformation did not add or remove entries and helps protect data integrity. If the row counts differ, raise an error because the transformed data should match the input size. This section checks how a Scikit-Learn preprocessing pipeline returns its results. It first confirms the Scikit-Learn version, then compares the default output, usually a NumPy array, with a pandas data frame output. It also verifies the transformed column names and inspects the first rounded row to confirm the preprocessing worked as expected. This script shows how Scikit-Learn pipelines can preserve feature names after transforming data with pandas. It compares the default output, which is a NumPy array, with a pandas data frame output that keeps readable column names after scaling numeric features and OneHotEncoding a categorical feature. The result makes transformed data easier to inspect while keeping the row count consistent, which helps maintain context in machine learning workflows. Feature name tracking. Feature name tracking helps keep machine learning models understandable and usable in production. As preprocessing transforms raw fields into new inputs, names preserve the connection to the original business meaning. This makes it easier for dashboards, APIs, and other systems to interpret model inputs and outputs, explain predictions, and diagnose problems reliably. Tracking feature names in production pipelines helps keep model inputs consistent from training through deployment and monitoring. It prevents silent errors when columns are reordered, renamed, or missing, which can lead to incorrect predictions even when the data appears similar. Clear feature names also make it easier for teams to verify transformations and discuss model behavior accurately. Tracking feature names is essential for making models understandable and maintainable in production. Clear names help explanation tools, drift detection systems, and stakeholders identify which factors influence predictions, such as in credit risk decisions. Without them, model explanations may be technically accurate but hard to use, weakening traceability, governance, and trust. Python code. Feature name tracking. Track transformed feature names, so production systems can correctly interpret pre-processed data. Pipelines help preserve feature meaning even when pre-processing changes the columns, and the output should align each transformed name with its value. We import pandas to work with tabular data and Scikit-Learn for machine learning tools. From Scikit-Learn, we use a ColumnTransformer to apply different pre-processing steps to different columns, a OneHotEncoder to prepare categorical data for models, and a StandardScaler to put numerical features on a comparable scale. A small customer dataset is created with pandas to make the example easy to inspect. It includes contract type, monthly charges, and tenure in months, giving both categorical and numerical features. This simple setup is used to demonstrate feature transformation and tracking. The data columns are separated by type, so each can receive the right pre-processing. Contract type is treated as categorical because it represents distinct groups, while monthly charges and tenure months are treated as numeric because they contain numerical values. This organization makes the plan transformations clearer and more explicit. A column transformer lets us pre-process different data types in one step. It OneHot encodes categorical columns into dense binary features and standardizes numeric columns so they have a mean of 0 and a standard deviation of 1. This ensures each column type is transformed in the appropriate way before modeling. The preprocessor is set to return pandas output, so the transformed data keeps clear feature names. It is then fitted to the customer data and applied in one step, producing a new data frame with the selected features properly encoded and scaled. Extract the transformed feature names from the preprocessor. Then compare them with the columns in the transformed data. If they do not match, raise an error to flag the mismatch. This check helps ensure the feature names stay aligned with the transformed data structure. This output checks the transformation by showing the Scikit-Learn version, the original data frame columns, and the number of features created. It then previews the transformed data by listing the first few feature names and displaying the first processed row with rounded values for easier reading. This script shows how to preserve feature names while pre-processing customer data in Scikit-Learn. It separates categorical and numeric columns, applies one-hot encoding and standard scaling with a ColumnTransformer, and returns the transformed result as a pandas data frame. It then verifies that the feature names match the transformed columns and reports key details such as the Scikit-Learn version, original columns, transformed feature count, sample feature names, and the first transformed row. This helps keep transformed data clear and consistent for production use. Array API handling. In production machine learning systems, arrays are often used because they are fast and simple, but they must be handled carefully. Unlike labeled tables, arrays do not show what each value represents, so the feature order, shape, and data types must exactly match what the model expects. Treating array handling as a design priority helps prevent mismatches that can lead to incorrect predictions. For reliable production data handling, define a clear contract between pre-processing and the systems that send or use the data. This contract should cover the expected feature count, feature order, categorical expansion, missing value handling, and numeric precision. Data must be transformed consistently into the same format used during training, because small mismatches in order or type can cause hidden prediction errors. Boundary checks for dimensions and value ranges help catch problems before the model scores new data. Modern production pipelines must handle different array formats reliably as models move from training to deployment. This includes working with dense, sparse, and labeled tabular outputs while avoiding costly conversions especially when many indicator features make sparse arrays more memory efficient. The key is to balance efficient computation with traceability, so array positions remain connected to the real-world features they represent. Python code, array API handling. This example shows how to protect the order of array features in production. Feature names define the expected input contract, and validation helps catch inputs that are missing or accidentally swapped. We import key Python tools for building a machine learning workflow: NumPy and pandas for data handling, and Scikit-Learn for modeling and preprocessing. Its setup includes tools to transform different columns, encode categorical features, scale numerical features, and combine these steps into a pipeline. It also imports logistic regression, which is used for binary classification. We create a pandas data frame to organize the training data with 3 features: age, balance, and segment. Age and balance store numeric information, while segment labels each individual as new, VIP, or standard. Keeping the data in this structured format preserves feature names and prepares it for consistent preprocessing and model training. The target variable is a small NumPy array of zeros and ones that represents the labels the model should predict. Because its values are fixed, it is useful for testing and validating model performance. Using a NumPy array also makes storing and working with these numeric labels efficient during training. A ColumnTransformer lets us apply different preprocessing steps to different types of data. In this setup, numeric features such as age and balance are standardized, so they share a common scale, while the categorical segment feature is converted with one-hot encoding. This keeps preprocessing consistent and ready to use within a machine learning pipeline. A pipeline combines preprocessing and model training into one workflow. In this case, the data is first scaled and encoded using the earlier preprocessor. Then, a logistic regression classifier is trained. The model uses a fixed random state for reproducibility and allows up to 200 iterations to help it converge. Fitting the model on the training data creates a contract based on the feature column names and their order. After training, these expected names are saved, so production data can be checked for the same structure. The preprocessing output names are also captured, showing how features are transformed and combined before they reach the model. A single production data point is first represented as a NumPy array containing age, balance, and segment values. It is then converted into a pandas data frame with the expected column names, so the data matches the model's required structure. This helps ensure the input is correctly organized before the model processes it. Before processing production data, the code verifies that the data has the expected number of columns. This confirms the input matches the structure the model was trained on. If the column count is wrong, it raises an error to prevent the model from receiving incorrectly formatted data. A small input array is created with values placed in the wrong order, then converted into a data frame with the expected column names. Although the data frame has the correct structure, the values no longer match the columns they belong to. This demonstrates why machine learning inputs must keep a consistent column order to avoid incorrect predictions. The code compares model predictions on correctly ordered production data and on data with swapped feature order, using the model's probability prediction method to estimate the positive class. This shows that changing feature order can change the model's output. It also applies the pipeline's preprocessing steps to the production data, so the inputs are properly formatted and scaled before prediction. This example checks the Scikit-Learn version, confirms the expected input column order, and shows how preprocessing changes the feature set and output shape. It then compares the model's positive class probability for correctly ordered data with the probability from swapped columns, showing that incorrect ordering can change predictions. The key lesson is to document array column order and validate inputs carefully to avoid data processing errors. This script shows how to use a Scikit-Learn pipeline to pre-process data and train a logistic regression classifier. Numeric features are scaled, categorical features are encoded, and the model is fitted in one consistent workflow. It then checks that production data uses the same feature order as the training data, because swapping columns can cause the model to misread inputs and change predicted probabilities. The main lesson is that feature order must be documented and validated carefully before using a model in production.
Capstone planning.
Choosing estimators. At the start of a capstone project, turn the problem into a modeling task that can be evaluated and used in practice. Choose a model type that fits the target, data, and decision needs, such as classification, regression, time series, or clustering, rather than defaulting to the most complex method. Start with a simple baseline, then compare stronger models using metrics that reflect real-world costs, such as emphasizing missed high-risk patients in medical screening instead of relying only on accuracy. Choose an estimator based on your data and practical constraints. Regularized linear models are useful when you have many numeric features but few observations, while tree-based ensembles can handle nonlinear patterns and mixed feature types with less feature engineering. For sparse, high-dimensional text data, use estimators suited to that representation. Justify the choice by considering data size, feature types, interpretability, training time, prediction speed, and fit with your preprocessing pipeline. In a capstone project, choosing an estimator should be an ongoing comparison, not a one-time choice. Test a few candidates with consistent validation methods, such as cross-validation, and tune hyperparameters carefully to avoid overfitting. The final estimator should fit the problem, data, validation plan, and real-world use, not just have the highest score. Python code. Choosing estimators. Use a single fair validation plan to compare estimators. Pipelines help prevent data leakage during preprocessing and modeling, and the results provide evidence for selecting the final capstone estimator. We import key Scikit-Learn tools to build and evaluate a classification workflow using the breast cancer dataset. A dummy classifier provides a simple baseline, while logistic regression serves as the main model. The data is split into training and testing sets, and balanced accuracy is used to evaluate performance fairly when classes are imbalanced. A pipeline with standard scaling helps prepare the features and train the model while reducing the risk of data leakage. We load Scikit-Learn's breast cancer dataset as an example for classification. The dataset is separated into input features and target labels, which prepares it for training and evaluating classification models. Before modeling, the code verifies that the feature data and target labels contain the same number of entries. This ensures every data point has a matching label, which is required for supervised learning. If they do not match, the code raises an error to catch the problem early and protect data integrity. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 1/4 of the data kept for testing. Stratification preserves the original class balance in both sets, supporting a fair evaluation. A fixed random state makes the split reproducible across runs. We first create a simple baseline using a dummy classifier that always predicts the most common class in the training data. After fitting it, we use it to predict the test data, giving us a benchmark for judging whether more advanced models perform better. The model pipeline first standardizes the features by centering them and scaling them to unit variance. Then applies logistic regression. It is trained on the training data, learning both the scaling settings and the classification model. The fitted pipeline then predicts labels for the test data, so the results can be compared with the true labels. We compare the baseline classifier and the logistic regression model using balanced accuracy on the same test labels. This metric accounts for class imbalance, making the comparison fairer. The model with the higher balanced accuracy is the more effective estimator under these conditions. The output first reports the Scikit-Learn version to support reproducibility, then identifies the task as a classification problem, and summarizes the dataset size and features. It compares the baseline balanced accuracy with the logistic regression pipeline's balanced accuracy. If the pipeline meets operational needs, it is recommended as the preferred estimator. This script compares a simple baseline model with logistic regression on the breast cancer dataset. It uses a stratified train-test split to preserve class balance, then evaluates both models with balanced accuracy. The baseline predicts the most common class, while logistic regression is trained in a pipeline with standard scaling to avoid data leakage. The script reports dataset information, the Scikit-Learn version, and both scores, recommending logistic regression if it performs better. Resource planning. Resource planning in machine learning means estimating what a project needs before modeling begins. For a Scikit-Learn capstone, this includes time, data access, computing power, storage, software setup, and human effort. A good plan starts with the prediction task, dataset size, preprocessing needs, and model complexity, while also accounting for limits such as budget or data access. Identifying these constraints early helps choose a realistic modeling strategy. When planning resources for a machine learning project, account for the full lifecycle, not just final model training. Data collection, cleaning, preprocessing, validation, and tuning can all add major time, memory, and compute costs. Plan experiments realistically and choose validation strategies that fit the domain, such as respecting clinical variables in healthcare or time order in retail forecasting. Resource planning in machine learning projects means assigning clear team roles, keeping work reproducible, and preparing for risks. Teams should use version control and consistent environments, while having fallback options such as smaller datasets or simpler models. Good evaluation planning, including reliable validation and error checks, helps support trustworthy conclusions. Overall, a strong plan guides both project management and quality assurance for a realistic Scikit-Learn workflow. Capstone project. A capstone project should be planned as a full production-oriented machine learning effort, not a set of isolated experiments. Begin by defining the problem clearly, including the data, prediction target, users, and decisions the model will support. Success depends on specifying what is being predicted, when predictions are made, what information is available at that time, and how different errors affect real-world outcomes. After defining the problem, build your capstone around a reproducible pipeline that carries data from raw inputs to final evaluation. Make clear how you handle missing values, categorical features, scaling, and feature names so the workflow is understandable and repeatable. Most importantly, prevent data leakage by using validation methods that respect time order or group boundaries. This structure shows not only how the model is trained, but also why its performance evaluation can be trusted. A strong capstone project should balance model performance with practical use. Students should choose appropriate metrics, explain their limits, compare a baseline with stronger models, and justify a model that generalizes well. The final choice should also consider speed, explainability, maintenance, and retraining, along with how inputs, outputs, errors, and future updates will be handled after development. Python code, capstone project. Plan the capstone workflow to prevent data leakage by keeping all preprocessing inside the validation folds. Then compare a simple baseline with a production-ready evaluation to judge model performance more reliably. We import key Scikit-Learn tools for a basic classification workflow, a built-in breast cancer dataset, a dummy classifier for a simple baseline, and logistic regression for a stronger binary classification model. We also include balanced accuracy to evaluate performance fairly across classes, a train test split to test on unseen data, and a pipeline to organize preprocessing and modeling. Finally, standard scaling is imported to normalize features before training. We load the built-in breast cancer classification dataset from Scikit-Learn in a structured format that is easy to analyze. The data is separated into input features, which contain the measurements used for prediction, and a target, which contains the diagnosis labels. This separation provides the basic setup needed to train and evaluate a machine learning model. The code first verifies that the number of feature rows matches the number of target labels, so every data point has a label. If they do not match, it raises an error to flag the problem. This check helps protect data integrity before supervised learning begins. The dataset is split into training and testing sets, so the model is evaluated on data it has not seen during training. Using Scikit-Learn's train test split, 25% of the data is reserved for testing. Stratification keeps the class proportions consistent, and a fixed random state makes the split reproducible. We create a simple baseline using a dummy classifier that always predicts the most common class from the training data, ignoring the input features. After setting a random state for reproducibility, we train it and use it to make predictions on the test data. These predictions provide a basic benchmark for comparing more advanced models. A pipeline keeps preprocessing and modeling consistent by combining feature scaling with logistic regression classification. The model is allowed enough iterations to converge. Then, the full pipeline is fitted on the training data, so scaling and learning happen together without data leakage. The fitted pipeline is then used to predict outcomes for the test data, which can be compared with the true results. We evaluate both models using balanced accuracy, which gives equal weight to each class by averaging recall across classes. This makes the comparison fair when the data is imbalanced. By calculating the score for the baseline model and the logistic regression pipeline, we can compare how well each model predicts both classes. The workflow begins by noting the Scikit-Learn version for reproducibility, then frames the task as predicting the diagnosis class before final evaluation. To prevent data leakage, the data is split before any preprocessing is fit inside the pipeline. The dummy classifier's balanced accuracy provides a baseline, while the pipeline's balanced accuracy shows how the logistic regression model performs. The final decision is to compare the model against the baseline before considering deployment, confirming that it adds value beyond a naive approach. This script shows how to evaluate a machine learning classifier while avoiding data leakage. Using the Scikit-Learn breast cancer dataset, it splits the data before preprocessing, then compares a simple, most frequent class baseline with a pipeline that scales the features and trains logistic regression. Both models are tested with balanced accuracy to account for class imbalance. The results provide a clear benchmark for judging whether the pipeline is strong enough for further deployment planning. In this lecture, you learned to design production-ready pipelines with consistent preprocessing and leakage prevention, use output configuration, feature names, and array handling to integrate with downstream systems, and plan and evaluate a capstone Scikit-Learn project from data framing to validation. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.